Okay, today we're going to do Unit 3, right? And last time we looked at electron configurations, and we used the alpha triangle and the alpha principle to write the electron configurations for various neutral atoms and ions. And we see that, or we saw by using those, excuse me, the alpha triangle, that the reasons why various atoms take on or lose electrons in order to get to the configuration of the nearest noble gas, which is termed the octet rule. Today we're going to look at ionic and covalent compounds, and also how to write formulas for ionic compounds, and then how to name them. So the ionic bonds, let's start here. Ionic bond. Now, an ionic bond is, these are electrostatic forces These are electrostatic forces of attraction. I can simplify that for you. It's opposites attract. That's what that means, right? 50-cent way of saying opposites attract. Electrostatic forces of attraction resulting from the transfer of electrons. So we actually have a transfer of electrons. Okay, ionic bonds are found in ionic compounds, of course. Ionic compounds okay, first of all, these are between a metal and a non-metal. So that's how you can tell right off the bat, right? We have our periodic table. We know that the left side of the periodic table contains the metals and the right side contains the non-metals. You'll have the formula right there in front of you. If you see a metal, it's an ionic compound. Okay, there are some exceptions. With the polyatomic ions, chromate and dichromate, they both have Cr in them, which are metals, but those are polyatomic ions which you memorize, right? You have to memorize all those polyatomic ions on page, I believe it's 3-5. Yes. You have to memorize all those polyatomic ions in the bottom of 3-5. Ionic compounds are metals and nonmetals, and they exist as crystal lattice structures. They exist as crystals. Okay? It's improper and incorrect to refer to any compound that contains a metal as a molecule. Doesn't exist. Okay? You've never heard of a molecule of salt, right? It's a crystal of salt. So we're not going to call anything with a metal a molecule. The term molecule is reserved for compounds containing only nonmetals, which we'll get to toward the end of today's lecture. Okay? Everybody good with that? Everybody cool? All right. So how do we form these ionic bonds? How do we form these electrostatic forces of attraction? Let's take a look at a simple example. Let's take sodium. Sodium with its 11 electrons. And let's take chlorine, because most of us are familiar with sodium chloride. And chlorine over here is 17. So we have 17 electrons. If I use my alpha triangle and do the electron configurations here, this is what the electron configurations for each of these two neutral atoms looks like. Right? Agreed? Well, if we look at this, we see that chlorine's valence configuration contains 7 electrons. It's outer shell. Not outer orbital. This is an orbital. The outer shell, in this case, is 3. So we have to add up all the electrons that have a shell 3. This is 7. That's why it's group 7. If we look up here at sodium, its outer shell is also 3. It's only got 1 electron in it. So you can see that if you move an electron, you can have a mutually beneficial transfer here. If we give up this electron down to the chlorine, then the 3s level will be gone, and we'll have an outer shell configuration now, because then our maximum or outer principal energy level would be 2, which means we'd have filled 8. This guy would take on that extra electron, and it would go to 8 as well. Everybody see that? And sodium is saying, you know, I haven't seen that 3s electron. It's way out there in the middle of nowhere. It's running around, getting in all kinds of trouble. Go ahead and take it. Okay? So the electron is transferred. The chlorine says, come on over here, little buddy. Here's our little friends. You can come on in here, and we'll have 8 in our outer shell. Both elements achieve an outer shell configuration of 8, an octet. So it happens. But because there was a transfer of an electron, they're going to take some charges, right? The metals want to lose electrons to get their octet. They get rid of their outer shell electrons so that they can realize their octet-filled principal energy level underneath. The nonmetals want to take on electrons so that they can fill their octet of their outermost principal energy level. So let's move the electron. Sodium plus. And Cl minus. Sodium plus now has 10 electrons. Cl minus has 18 electrons. Notice that both now have satisfied their octet. They both have 8 electrons in their outermost principal energy level. But now they carry a charge. Okay? And now physics takes over. Opposites attract. Okay? So the actual ionic bond is opposites, bless you, is the opposites attract. Okay? How did the opposite charges come about? They came about because an electron was moved around from one to the other. The metals want to give them up, the non-metals want to take them. Okay? If we were to show this using Lewis, okay, we would say sodium, what group number is it in? 1. It's 1. So it's only got 1 electron. Chlorine is in group 7. 1, 2, 3, 4, 5, 6, 7. This electron will move over. We'll go sodium plus. Cl minus with what is now 8 dots. Now these opposites attract and you get NaCl. This is how we would show it with Lewis. Remember, Lewis configurations, Lewis diagrams only show the outer shell or valence electrons. Basically the group number from the periodic table. Okay? Everybody see that? All right. So, how do we write formulas for these ionic compounds? We know that group numbers tell us a valence configuration, and that once we know that, we can make predictions about what the oxidation states of those elements are going to be. So, group number 1 are going to be +1s, group number 2s are going to be +2. We're going to skip the transition series for now. We're going to go to group 3, they're going to be +3s. Group 4, that's a carbon, we're going to wait on that for a couple of weeks. Group 5s want to be -3. Group 6 is -2, group 7 is -1. Okay, and of course group 8 is 0. So if we know that, we can write our formulas for ionic compounds. Now first of all, compounds are neutral. All right, they have an overall net 0 charge. They're neutral. When we look at forming or writing formulas, we want to make sure that overall there's no charge. So let's write the formula. We'll start with an example. Okay, binary. What's binary mean? 2, right? It's 2. So right now we're only talking about compounds that contain 2 types of elements. Not 2 total, just 2 types. So you can have, for example, MgCl2. This only contains magnesium and chloride. But that's 2. That's why it's binary. And we look at the capital letters, right? All of our elements start with a capital letter. So we look and see how many capital letters we have. If we have 2 capital letters, this is a binary compound. If it has more than 2 capital letters, we're jumping ahead just a little bit. But if it has more than 2 capital letters, there's a polyatomic ion in there, and you have to be able to recognize it. Okay? So let's look at combining. Let's say Na and Cl. I know we already know this one, we just did it. Sodium is in group number 1. Okay, and remember, there's a difference between how the element exists in nature and how it exists in its most stable form. Sodium exists in nature neutral. It's got no charge on it. But its most stable form is +1 because it's in group 1. Okay? And the reason why it doesn't exist in nature in its most stable form is because it can't hold this charge indefinitely. It costs energy to hold this charge. And it doesn't have an infinite supply of energy. So, everything in the natural state is neutral. Right? Doesn't mean that it's its most stable. Cl is group 7, and group 7s are -1. These are neutral. They cancel each other out in 1-to-1 ratios. So our formula is NaCl. What if we wanted to do aluminum and oxygen? What if we wanted to do aluminum and oxygen? What's the charge on aluminum? 3 plus, very good. What about oxygen? 2 negative. Now, these have to be neutral, and they're not, right? I know there's a crisscross method where you can do this and do that. Don't do that. You're going to get in trouble. All right, this method works all the time. It's quick, it's easy. Do it this way, right? These have to cancel each other out, and those of you can already see maybe there's a common factor of 6 here, so you already know where you're going. But I'm not that smart, so I look and I say negative 2, positive 3. I'm deficient on the negative side. I need more negatives. But I can only add O to negatives. I can't add this. I can't say, oh, there it is, negative 3 plus 3. Because O only comes in 2 negative. Now I have negative 4 plus 3. Now I'm deficient on this side. But I can only add aluminums in a plus 3 charge. 3 plus. Plus 6 minus 4. I'm deficient on the negative side again. And you just keep going back and forth until eventually negative 6, positive 6, they're neutral. In order for that to happen, I needed 2 aluminums, I put that as a subscript, and 3 oxygens. That's how I write my formula. Everybody see that? How about calcium and nitrogen? Calcium and nitrogen. Got it? Everybody got an answer? Yeah? What is it? What is it? Right? Everybody got that? And remember, you know why this plus 3 is there. You know why this is minus 2. Because if you look at the electron configuration, oxygen needs 2 electrons to achieve its octet. If it takes 2 electrons over neutral, it goes negative 2. Aluminum wants to give up 3 to achieve its octet. If it goes 3 negatives, it gets rid of 3 negatives, it takes on plus 3. So it's not rocket science where these charges come from. Okay? And all we have to do is make sure we put them together in the correct ratios. All right, to make it neutral. All right? Okay. Name. We do naming now. Nomenclature. Okay, we're going to name some compounds, and you have to have a procedure for doing this, okay? I'm going to give you a flow chart, and you're going to say that every time you see a compound, you're going to go through binary compound, yes, metal present, yes, metal transition, yeah, name it, right? You have to have a system, otherwise you're going to mix them all up. You're going to put prefixes with metals, you're going to put Roman numerals with non-metals. I mean, you need a procedure. Before we name the compounds, however, we have to make sure that we can name the elements, and we can name the cations and anions that are formed from those elements. So, first thing, we're going to use IUPAC. IUPAC is the International Union of Pure and Applied Chemistry. Okay? It's an organization that gets together and discusses rules for naming compounds worldwide. That's so scientists in Germany can name compounds and scientists in the United States will understand what they're talking about. Must be really exciting, right? They go to exotic places, so that's kind of cool. But imagine a bunch of guys sitting around talking about rules for naming. IUPAC says that the elemental name is reserved for that element as it exists in nature. Okay? Which means when you memorize that first table on first page of Unit 2, and you memorize magnesium, that name is reserved for magnesium, how it exists in nature. Its natural form. Okay? The elemental name is reserved for the element as it exists in nature. So if we were to take something like this would be magnesium. But how do we differentiate that from this form of magnesium? We obviously have to have a different name, right? This is magnesium ion. It's magnesium ion. Whenever you have a cation, remember cations are positive, right? It's got a little plus sign right in it, right? Whenever you have a positive or a cation, it's the name of the element with the word ion attached to it. Okay? So any positive ion, just it's the name of the element plus the word ion. So what's this? Hydrogen ion. Lithium ion, right? I can't do anything for you. I can't help you if you do not know that Li is lithium. You have to know those symbols. And it's not going to come to you. You're not going to stare at it and say, oh, sooner or later it's going to come to me. Like something might in a math test or something because you had it in high school. You can stare at some of these as long as you want. If you did not memorize them, it's not going to miraculously jump into your head. Even though it's a multiple choice exam. Okay? So you got to pay your dues. Everybody's done it. I did it. You'll do it. It's just a rite of passage. You got to memorize those symbols. Okay? You have to know. All right. So what about the anions? What about anions? What about anions? All right. What was your question?
I was just asking if you're bromine.
Yeah. It's not bromine.
Bromine.
But
Oh.
when they have a negative sign, they're going to end in IDE. This is this root plus IDE for anions. So cations are the element's name plus the word ion. The anions are named with this root plus IDE. The problem is that getting the root is not all it's cracked up to be. All right? And I'd like to say, well, it just looks right. But right now, I wouldn't imagine not much looks right when it comes to writing names down, right? So F minus would be fluoride. Chloride. Bromide. Iodide. N minus 3, nitride, S2 minus, sulfide. Unfortunately, there's no consistent rule where I could say, look, take the element's name, drop off the UR, add IDE. It doesn't work that way. You just have to get a feel. Now, these are somewhat well behaved, and this is group 7, right, which are the halogens. The halogens are well behaved. They kind of all do the same thing. But outside of that, it doesn't really apply. Nitrogen becomes nitride. Oxygen becomes oxide. Sulfur becomes sulfide. I mean, you just have to kind of get a feel from using, right? Again, it is multiple choice, so you should be able to pick them out. We're not going to have choices on there that's iodide and then change one letter and have it also ending in IDE. We won't do that to you. Okay? All right? Okay. There are some elements that exist in nature as pairs. Okay? These are called the diatomic molecules. And they are molecules. Right? They're nonmetals. There are 7 of them. The diatomic molecules. And the way I always remember them, since there are 7, everybody have their periodic table out. They start at nitrogen, which is atomic number 7, right? Go 3 over and 3 down. So we've got N2, O2, F2. That's our 3 over. And our 3 down are going to be Cl2, Br2, and I2. And I know you're saying, well, that's only 6. Well, then we have hydrogen, H2. These are the 7 diatomic molecules. Now, there's a lot of inconsistency when it comes to naming these. There's 2 groups of people. They do pretty much, whatever they want. But IUPAC is explicit. They say the name of the element is reserved for that form in nature. This is how they exist in nature. So when you say oxygen, this is what you're talking about, O2. Unfortunately, some people don't follow the rules, and they call it diatomic oxygen. Okay, but technically that's not correct. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. And when they break them apart, so if you have O2, this is oxygen. O would be atomic oxygen. And of course, O2 minus would be oxide. So let's look at this. So we've got 4. What is it? You see it before? Have you seen that before? Usually you can get the first three, but the last one's a little. What's this? Hydrogen. What's this? Atomic hydrogen. What's this? Hydrogen ion. What's this? It's hydride, right? Hydroxide is this, right? How do you know that? Because you memorized it. It's the only way you know. Okay? That's hydroxide. So this is hydrogen. That's a Y, believe it or not. This is atomic hydrogen. Or monoatomic hydrogen. This is hydrogen ion. And lastly, we have hydride. Notice the IDE ending is consistent with a negative. Yes?
Is it hydride ion?
No. You don't use the word ion with negatives. You can, but it's probably that way in the book, right?
Yeah.
Yeah, don't. I mean, you could. When you name them, it's not going to be that way. It's going to be potassium hydride. The negative form ends in IDE, and that's what tells you that it's a negative. It's not incorrect to put ion. And technically, anytime you have an ion, you could put the word ion on there and not be incorrect. Even with the polyatomic ions, it could be hydroxide ion or phosphate ion. So anytime you have a charge, you can follow it up with the word ion. I don't necessarily like putting the word ion after the negative one because that's really the differentiation for the cation is the word ion. So I don't want to have two things up here that have the same word. But it's definitely not incorrect. On the exam, if you had this, it would say the answer would be hydride, not hydride ion. If you saw SO4 2-, it would be sulfate, not sulfate ion. Because it's kind of implied that it's already charged, so everybody knows it's an ion. Okay, if you look at the bonding, and these are molecules, right? These are molecules, they're non-metals. These are diatomic molecules. They all have single bonds between them, except the nitrogen, which has a triple bond, and the oxygen, which has a double bond. Everything else is single bond. And we're not surprised by that, because if you look at nitrogen's Lewis, right? It's group 5. It wants to have 3 bonds. And if it's bound to another nitrogen, that nitrogen also wants to have 3 bonds. That's where triple bond comes from. Right? Oxygen, you can use the same logic for oxygen. All of these guys only have 1 electron, which means they can only form 1 bond. Fluorine, chlorine, bromine, and iodine are group 7s. They still have 1 bond and 3 lone pairs. Hydrogen's group 1, so it's only got a single bond. Okay? These guys are multiple bonds, doubles and triples. Okay. So, how do we name our compounds? So I'll give you a flow chart. So you can ask yourself a series of questions. And the first question is it a binary compound? Do I have a binary compound? And remember, binary means 2, but in this case it means 2 types of elements. Okay? You can have 10 atoms, still a binary compound. if there's only two of them. P4O10. Capital, capital, this is still a binary compound despite the fact that it has actually 14 atoms. Okay? So, first question we're going to ask is binary compound. If the answer is yes, we'll deal with no in a little bit. We're going to ask, is there a metal present? Is there a metal? Since we'll be looking at the formula, and we have the periodic table, we're going to know if there's a metal. Is it anything from the left side of the periodic table, left side of that division point? Yes. Next thing we're going to ask is, oops. The next thing we're going to ask is, does the metal have only a single possible oxidation state? And by the way, oxidation states are those plus 1s, plus 2s, plus 3s, minus 2s, minus 1s. They're those numbers that we were assigning to the ions when we formed them. Okay? If our answer is yes, then this is probably more likely a group 1, 2, or 3, group 3 metal. Most of the group 3 metals. Okay, we could alternatively say here, is it a group 1, 2, or 3 metal? Or is it a transition metal? Is it not a transition? If it has only one, we're going to name the cation first. Name the anion second. And that's okay, because that's the way we wrote them. Remember when we were writing our formulas for aluminum and oxygen and magnesium and chlorine? We always wrote the metal first, the cation, and we wrote the nonmetal second. So the cation is written first, it's named first. The anion is written second, named second. We are going to name the cation using its elemental name. That means we're going to drop the word ion from the cation name. We're going to name the cation using its elemental name. We're going to name the anion root plus IDE. Can you see that in the back? Barely. Okay? So let's do some examples. Binary compound. Yes. Is there a metal present? Yes. Does the metal have only one possible oxidation state? Where is it? Group 1, right? It's in group 1. So group 1s can only be plus 1. Name it. Potassium oxide. We named the cation using its elemental name, the anion root plus IDE. And this would have worked out if we wanted to write the formula, right? -2 plus 1, they're not equal. I need more positives. Plus 2 minus 2. That's where it came from. I can modify this a little bit. Is it a group 1, 2, or 3? Is it not a transition metal? Binary compound? Yep. Metal present? Yep. Does the metal have one possible oxidation state? It's in group 2? Yep. Name it. Magnesium sulfide. IDE. Okay. What if our answer here is no? What if the metal has more than one possible oxidation state? All right, everybody look at your periodic table. At the bottom of your periodic table, there are a list of metals. Those metals have more than one possible oxidation state. They are transition metals. Okay? Those are the only ones we want you to be familiar with, but they're not the only ones that have multiple positive values. In the transition series, all metals that have multiple possible oxidation states, that's where they're located, in the transition series. But unfortunately, not all the elements in the transition series have multiple positive oxidation numbers. In other words, there are some transition metals that are as well behaved as sodium or potassium. Zinc, for example. Zinc is in the transition series, but it can only be +2. Okay? About half, roughly half of those metals have multiple positive oxidation possibilities. All the other ones are very well behaved. Okay? IUPAC used to say, look, anytime you have a metal, you have to tell us what the charge on the metal is using Roman numerals. You have to do it. But then someone said, well, if I have sodium chloride here, why do I have to call it sodium 1 chloride, indicating that it's +1? Because sodium can't be any other charge. It can only be +1. So why do I have to specify? So they changed the rule around. And now, when you have a metal with multiple possible values, you have to use Roman numerals to indicate what the charge is on that unusual metal. Let's see. Let's see an example. Knowing what we know right now, let's look at FeO and Fe2O3. Fe is iron. Okay. Knowing what we know, what would you name the first one?
You would name it iron oxide.
Iron oxide, right? What would you name the second one? Iron oxide, right? clearly these are not the same compound. So we have to have some way to differentiate between the two. Okay? We look on our periodic table and we see that iron is one of those elements at the bottom of the list. Iron is one of those metals that is capable of having multiple positive values. It can be iron 2 or iron 3. We have to say in the name what the form or what the charge is on the iron. How do we do that? The iron is misbehaving. We don't know what its charge is. But we do know what oxygen is. And we know that when they combine together, they're neutral. So we use this fact to determine what the charge on the iron is. I don't know what iron is, but I know what this is. What is it? 2 what?
Negative.
Negative 2, right. 2 negative. How many do I have in the formula? 1. Which means my total negative is negative 2. In order for this to be neutral, my total positive must be positive 2 to make that neutral. How many irons do I have to come up with that positive 2 charge? From the formula, 1. This is iron 2 oxide. Notice here there is no space. You go right into the parentheses. There's no space there. The Roman numeral is used to tell you what the charge on the transition metal is, because you don't know what it is. It's not like magnesium, which is in group number 2, so I know what its charge is. Iron can have multiple possibilities, so we have to figure out what it is. Let's apply the same thing over here. I see the iron's there. I don't know what form I have, but I do know that it's combining with a very well-behaved anion. So what is oxygen's charge? It's still negative 2. How many oxygens do I have in the formula? 3. Right? My total is negative 6. If this is a compound, which it is, it must be neutral. So my total positive must be positive 6. Right? How many irons do I have to generate that total positive 6 charge? I have 2 ions to come up with that positive 6 charge, which means each iron must be plus 3. This is iron 3 oxide. On the exam, when you see those elements on the bottom, the very bottom of the page containing the periodic table, very bottom, very bottom, very bottom, the very bottom, does everybody see them? Roman numerals. If you see any of those elements, you've got to have a Roman numeral in the name. So if we say no, does the metal have only one possible oxidation state? We're going to follow these same rules, with the exception that we have to put in a Roman numeral to tell what the oxidation state of the metal is. Roman numeral is included in the name so that you know what the positive charge is on the metal. The Roman numeral does not tell you how many you have. It doesn't tell you how many of the particular irons or coppers that you have. It tells you the charge. Binary compound, metal present, yep. Is the metal group 1, 2, or 3? Nope. Is that one of those metals on the bottom of our periodic table? Yep. So what is it?
Cobalt 2 chloride.
Cobalt 2 chloride. Everybody see that? Chloride is -1. I have 2 of them, -2. This must be +2. The formula shows only 1 cobalt. This is cobalt 2 chloride. Binary compound? Yep. Metal present? Yep. Metal have more than one, or metal have one possible oxidation state? Nope. What is it? Tin 4 or tin 2? It's tin 4, right? Anybody put tin 2? Nobody put tin 2? Tin? Don't know what the charge on the tin is. I know that there's 2 possibilities, 2 or 4. I do know the charge on oxygen is -2. Grand total -4 because I have 2 of them. This is a neutral compound, so the total positive has to be +4. There's only 1 tin indicated in the formula. This is tin 4 oxide. You also have to be able to go the other way. That is, given the name, you have to be able to write the formula, right? But for these ones, it's pretty straightforward because they're telling you what the charge already is on the particular transition metal. So if I had lead 4 bromide, if I had lead 4 bromide and I wanted you to write the formula, what would I do? First of all, you got to know the symbol for lead, don't you? What is it? PB, very good. PB, there's the charge. You don't even have to look it up. Gave it to you. Bromide, group 7, right? Wants to be -1, right? Everybody see that? These obviously aren't equal. I'm deficient on the negative, -2, still deficient, still deficient, There it is. 1 lead, 4 bromides. PbBr4. Got to be able to go both ways. I'm going to give you the name, you got to come up with a formula. I'm going to give you the formula, you got to come up with a name. Everybody good?
Can we do one more like that?
Sure. Where I give you the name? Copper 3 sulfide. Yeah.
But copper can only be 1 or 2.
Oh yeah. And cobalt. Then cobalt. Got an answer? What is it?
CO2, S3.
Yep. Everybody got that? And you could really, it only takes a second, right? As long as you have this written down, go ahead and name it and see if you get this name. So it's kind of self-checking. Once you have the name, you can rewrite the formula and make sure that that you get what you started with. So it's very easy to check these naming. Okay. Okay, how about if there's a metal present up here, the answer is no. Metal present, no. We're going to use prefixes. Again, we're going to follow, all of them follow this same basic format. We're going to name the cation first, the anion second. We're going to name the cation with its elemental name. We're going to name the anion with root plus IDE. But we're adding on to them with just a little extension of this protocol right here. We have prefixes. Mono is 1. Di is 2. Tri is 3. Tetra. Penta. Hexa. 6. Hepta. Octa. Nona. And deca. These are the prefixes that we will attach to the names. And you have to memorize them. Now, all of these prefixes end in a vowel. They're either O's, I's, A's, right? And sometimes you're going to run into anions that begin with a vowel. So you're going to drop them under certain circumstances. And we'll see some examples right here. How about N2O5? Is this a binary compound? Yes. Is there a metal present? No. Prefixes. Dinitrogen pentoxide. Now, if the prefix ends in an A or an O, which is all of them except for di and tri, right? And the name of the element begins with a vowel, then you drop the A or the O from the prefix. But you're not going to have an example like this is dinitrogen. Pentoxide. You're not going to have another choice that says pentaoxide. Okay? It's not going to be that particular. But notice that this ended with an A. The name started with an O, so we dropped the A from the prefix. It's pentoxide, decoxide. It's not pentaoxide. Okay? Or tetraoxide, tetroxide. Now there is one exception. With CO2. Carbon dioxide, most of us know that, right? It's bubbles and fizz in our soda. Notice that we only have one carbon here, but we didn't say monocarbon dioxide. You never use mono with the first element. You never use mono with the first. You can use it with the second though, right? CO is carbon monoxide. Right? So use prefixes. I'm saying cation and anion here, but technically that's not correct because these aren't necessarily the result of cations and anions. These are covalent. These are covalent bonds, so the electrons are being shared. There's not a transfer of electrons resulting in a plus and minus, but we'll stay with the first one, right, with the cation. The first element. You never use mono. But you always remember that because you know carbon dioxide. It's not monocarbon dioxide. And you know you use it with the second one because it's carbon monoxide. Now, these are just straightforward naming, right? And when you're given the name, it's even easier with the covalent compounds because you just write down whatever's given, right? If you have one that says carbon tetrachloride, if you have carbon tetrachloride, you just write it down. Carbon tetra 4 chlorides. You don't go to the periodic table and get positives and negatives and go back and forth until you get the formula. You just write down whatever you're given. All right? Now the last one is binary compound. What if you say no to binary compound? If you say no to binary compound, you have a polyatomic ion. you have an ion off that list on page 3.5. And the only way you're going to know how to name it is if you memorize that list on 3.5. Polyatomic ions, literally, poly, many, many atom ions. That's what they are. Notice that all of them are negative except for NH4, ammonium. Might help you a little bit. The good thing about polyatomic ions or compounds containing polyatomic ions is you just name them. You just name them. So you can have MgSO4. Binary compound? What? Is it a binary compound? No, it's not, right? I see three capital letters. M, S, and O. That's not a binary compound. Do you see the polyatomic ion in there? Do you? Yeah, it's SO4, right? Name it. Magnesium sulfate. Magnesium sulfate. I can't get a good pen. Oh, there's one. Magnesium sulfate. Elements containing polyatomic ions. You just have to memorize them. You have to know. Binary compound? Nope. But what is that? What is that copper? What?
Copper sulfate.
Can't be copper sulfate. Look at it. What is it? Is copper one of the elements on the bottom of that of your periodic table? It is, right? It's one of those metals that have multiple positive oxidation states. So we have to include the Roman numeral in the name. Whenever you see those elements at the bottom of that list, you will have a Roman numeral to name it. It will be included in the name. You follow the same procedure, right? I don't know what copper is, but do I know what sulfate is? Yes, I do. How do I know that? Because you memorized it. That's the only way you're going to know it. You have to know how to write the formula for the polyatomic ion, you have to know the name of the polyatomic ion, and you have to know its charge. Sorry. Sulfate is -2. Which means if this is a compound, my total positive charge has to be +2. How many coppers do I have to come up with that +2 charge? 2. That makes each one of them what? More +1, right? +1. So this is copper 1. Sulfate. This one, of course, is copper 2. What if I want to write a formula? Calcium hydroxide. I want to write a formula involving a polyatomic ion. I have to know what it is, don't I? Calcium. What is it? Charge? Hydroxide. What is it? OH minus, right? I have to get these to be neutral. I have a +2 here and a -1 there. I'm deficient on the negative side, so I need more of them. But I can only add hydroxides in increments of -1. -1 minus 1, that's -2. Cancels a +2. Ca, but now I need 2 hydroxides, right? I don't do this. I don't do this. This says 1 calcium, 1 oxygen, 1 hydrogen. I need 2 hydroxides. So I put them in parentheses. Whenever you have a formula that has multiple copies of the polyatomic ion, you must put the polyatomic ion, the entire polyatomic ion, in parentheses. This formula has 1 calcium and 2 hydroxides, and that's what this shows. But when you only have a single one, like sodium hydroxide, for example, you don't put it in parentheses if you only have 1. You only do it if you have more than 1. Alright? We're going to get a whole lot of work using all of these versions in lab today, lab number 3. That's all it is naming. Naming, naming, naming. Write the formula. Name, write the formula. So we're going to get a lot of practice in a little bit. Alright? You have to have a procedure though. Alright? Binary compound. Yes. Metal present. Yes. Is the metal group 1, 2, or 3? Yes. Name the cation by its elemental name, the anion root plus IDE. Is the metal a transition metal? Is it not group 1, 2, or 3? No, it's not group 1, 2, or 3. Roman numerals. Binary compound, yes. Metal present, no. Prefixes. Binary compound, no. Polyatomic ions. This is really the only way to do it, because otherwise you're going to be doing all kinds of things. You're going to be doing all kinds of ridiculous things, right? For example, NO3. What is it? What is it? Nitrate? No, this is nitrogen trioxide. This is nitrate. Alright? Be careful. Be careful, okay? Now, there are prefixes used with metals in the polyatomic ion, but you never use prefixes with metals. In fact, in order for you to even use the prefix, you have to say metal present? No. But the polyatomic ion, dichromate, does have a prefix with a metal. But guess what? These are rules for naming compounds, which are neutral species. They're not rules for naming polyatomic ions. The ions, you know the rule for naming ions is? Memorize it, right? That's the rule. Alright? Everybody good? Okay. So there's our naming. You do need to know that for the exam. You will be tested. Okay, we talked at the beginning, we began the lecture with an ionic bond and ionic compounds. So now we're going to move to the covalent. Covalent bond. Okay, this is a bond formed by sharing electrons. You're going to share electrons in the covalent bond. Now, covalent bonds are part of covalent molecules. So, for covalent molecules, covalent compounds, this is between two nonmetals. And they do exist as molecules. They exist as molecules. Let's look at the simplest or smallest covalent compound, hydrogen atom. Sorry, hydrogen molecule. This is a hydrogen atom. This is another hydrogen atom. Okay? These two hydrogen atoms will approach each other. And they'll approach each other and approach each other and approach each other. And the nucleus is positively charged because it contains the only charged particle in the nucleus is a proton. There's neutrons, but they're not charged. So they'll meet this minimum distance. They'll hit this minimum distance between the two nuclei, where this electron will start to feel the positive pulling power of this nucleus. And this electron will start to feel the positive pulling power of this nucleus. Okay? And when they do that, this hydrogen atom is going to say, well, I don't have a strong enough electronegativity to take your electron away, but you're not getting mine either. And this hydrogen atom says, well, I feel the same way. Because their electronegativities are identical, they don't have enough electron pulling power to rip the electron off one of the other atoms. As a result, the electrons begin to rotate or orbit around both nuclei. And that's what creates the bond. These outer shell electrons, these valence electrons to two individual nuclei, are now valence electrons to two nuclei. They are covalents. And that's where the name of the bond comes from. It's a covalent bond. The electrons actually start orbiting both nuclei. And it's the electrons revolving around both nuclei that actually create the bond that hold the nuclei together. It's not like Ionic, where we actually had a transfer of electrons which resulted in a positive and negative charge, and then opposites attracted. These are actually being orbited by electrons. It's a covalent bond. Okay? Now, since these are both, this is a H2 molecule now. That's a hydrogen molecule now. These electrons are chasing each other around. Okay? They're repelling, because like charges repel. And they're flying around this. So at any given time, you could say there's perfect symmetry in the orbit of the electrons. In reality, there isn't. Okay? There isn't. There's these London forces and van der Waals forces that say, no, there are temporary, statistically predicted dipoles in here. But we're not going to deal with that right now. For now, we're going to say, look, these guys are just rotating around these two nuclei, maintaining the exact same distance from each other, basically repelling each other around. Okay? So, there's no asymmetric distribution of the electrons. The electrons are perfectly symmetric between the two nuclei. And therefore, there's no pole. There's no magnet. Right? So this is non-polar. This is non-polar. There's no magnetic dipole in any of the diatomics. I guess I shouldn't say that. Okay? The electrons are perfectly symmetric between them. There's an exception to that. But what happens if you have two nonmetals that aren't the same nonmetal? Carbon and oxygen, for example. These are two nonmetals. They're located on the right side of the periodic table, and they're not the same nonmetal. They're different nonmetals. Okay? They have different electronegativities. Right? Again, electronegativity is this property that measures an element's capacity to draw electron charge toward itself. More simply stated, it's a measure of an element's desire for electrons. It's how much it wants electrons. Now, we already know that the nonmetals should be highly electronegative because the nonmetals, according to the alpha and electron configuration, nonmetals always take on electrons to complete their octet. The metals give them up. So the nonmetals are relatively electronegative. They're strongly electronegative. They want electrons so that they can complete their octet. The most electronegative element on the periodic table is fluorine. The closer you are to fluorine, the more electronegative you are. All elements have different electronegativities. No two elements on the periodic table have the same electronegativity. So, when you put two different nonmetals together, there's basically a tug of war for the electrons between them. And the tug of war is won by the element that's closer to fluorine, the more electronegative one. So, if we compare carbon and oxygen, looking at your periodic table, which one's closer to fluorine? Oxygen. So oxygen is more electronegative. So instead of having a nice symmetric orbit around the two nuclei, the orbit, the electron's movement is distorted because of the more highly electronegative oxygen. And it's distorted in such a way that the electron ends up spending a little bit more time around the oxygen than it does around the carbon. We have an uneven distribution of electrons, and therefore we have polarity. Now, this is nothing like we saw earlier for the ionic compound, where you actually had a transfer of electrons. You actually moved an electron, and you created a full positive and a full negative. This isn't anywhere close to that. This is just a little bit negative because the electron spends just a little bit more time orbiting the oxygen than it does the carbon. So we show this with a Greek delta. In our language, we have a capital D and a lowercase d in our alphabet. In the Greek alphabet, they have capital D's and lowercase d's. This is a Greek delta, and it means slightly. It's just a little bit negative, little bit positive. Anytime you have two nonmetals that are different nonmetals, you will have a polar bond. You have a polar bond. Because of the difference in electronegativity, each element affects the orbiting electrons differently. The more highly electronegative element wins the battle and pulls them a little bit more towards itself, which creates a pole, a dipole, north and south pole. Okay? Anytime you hear the word polarity, dipole, dipole moment, dipolar, anything like that, think about a simple bar magnet. Just think about a simple little magnet, little north-south pole magnet. The bond behaves just like it. It'll line up in a magnetic field. It will be opposites attract. It'll be attracted to other molecules that they're slightly negative, and positive regions will be attracted to each other. It behaves just like a magnet. Okay? There's actually a force vector associated with this. There's a vector associated with it, and you could actually draw in the vector. You draw the vector in the direction that the electrons are being pulled. It actually has a magnitude and a direction. And you cross the back, indicating that this is the positive side of the vector. That positive side. So you can actually draw it. It has a magnitude. Okay? Now, covalent compounds exist as molecules. And those molecules have defined structures. How do we know what those structures are? Well, we're going to go back a little bit to our Lewis dot. Okay? If we look at carbon, and we say carbon is in group 4, and we put our Lewis dots in, 1, 2, 3, 4, and we say nitrogen is in group 5, 1, 2, 3, 4, 5, and oxygen is in group 6, 1, 2, 3, 4, 5, 6. We look at this and we see every place there's a single electron. This is a bonding position. So carbon has 4 electrons, 4 bonds. Nitrogen has 3 bonds and 1 lone pair. We call these lone pair electrons. They're not antibonding. They don't take part in bonding. They don't really affect it. They certainly don't work against it in an antibonding fashion. And then, of course, oxygen has 2 bonds and 2 lone pairs. We then have to go to our little diagram. On page 313. 313, the one that has our shapes. We look at carbon and we say, how many bonds does carbon have? 4. How many lone pairs? 0. So look at bonding atoms 4, lone pairs 0, and you see that in this configuration, when carbon is a central bonding atom, it will be a tetrahedral. Do you see that? What about nitrogen? 3 bonds, 1 lone pair. What is it? Trigonal pyramidal, trigonal pyramidal, depending on where you're from. Oxygen, 2 bonds, 2 lone pairs. What is it? Angular or bent. So you will have a question on the exam on this. Okay? And it'll probably be one of those actual examples. If we know something about the geometry, we can make a prediction about whether the molecule is polar or not. You can have polar bonds in non-polar molecules. If the polar bonds, remember we could draw a little vector. If they're 180 degrees to each other, they'll cancel each other out. It's kind of like 2 cars hooked together with a chain, and they're floored, the same car going opposite directions. Nothing's going to happen. because they exactly cancel each other out. So if you have that kind of situation, where you have, for example, a linear molecule, then those vectors are going to cancel each other out. So you'll have a nonpolar molecule. For us, in here, your only possibilities for nonpolar, only possibilities, you can write them right here on this table, the tetrahedral and the angular. Those are the only nonpolar possibilities we have. All the other ones, did I say angular? No, linear, sorry. I was looking at angular. Linear and tetrahedral. Linear and tetrahedral are the only possibilities for nonpolar. All the other ones will be polar. If you have a bent, let's say we're going to do water, for example, and oxygen is closer to fluorine, right? So our bond looks like this, negative, positive, because both of the bonds are polar. Oxygen's closer to fluorine, I know this should be the same length. So our vectors are going this way, right? They're going to hit each other, and there's a net result. Bang, it's still going to go forward. It's like two cars smashing into each other at an angle. They don't stop, they keep going afterwards. If there's a net result, then the molecule itself is polar. If there isn't a net result, like two cars smashing each other head on, boom, they stop. No net result. Nonpolar. Our possible configurations, at least the ones we've defined for you, only the linear and only the tetrahedral have possibilities of giving you nonpolar molecules. That's it. All the other ones will be polar. Right? So if you have nonmetals, and they're different nonmetals, you have polar bonds, for sure. You have polar bonds. If your geometry is linear or tetrahedral on those polar bonds, the molecule itself is nonpolar. It doesn't react in a magnetic field. Right? They cancel each other out. The polarities cancel each other out. Every other configuration will result in a polar molecule. Polar bonds, polar molecules. Questions? Questions? Okay.